Hello everyone, my name is Karepalo and this is a presentation about our paper OpenASIP 2.0 Co-Design Toolset for RISC-V application-specific instruction set processors. And here is the list of contents of the presentation. First, we go through the motivation behind this work. Then we discuss OpenASIP background. And after that, we go through the features that we added in this work. And those include RISC-V Customization in the toolset, as well as a hardware generation tool called Function Unit Generator. After that, we go through the design case studies that we included in the paper, and then we go through the conclusions. But first, let's discuss about the motivation behind the work. The biggest motivation behind this work is that RISC-V and open source hardware have become very popular in the recent years. And in addition, there is a demand for customized processors to achieve better performance or energy efficiency in the target application. But however, designing and programming customized processors is difficult and error-prone work. So hardware and software co-design toolsets are required to make it easier. Despite this, current RISC-V co-design toolsets are proprietary, such as ASIP Designer, CodeASIP, and Andes. Contrary to other toolsets, we implement our RISC-V customization flow on top of our previous open source work called OpenASIP. OpenASIP has been developed for around 20 years, so it is quite a mature project already, which serves as a good base for RISC-V customization. The architecture traditionally used in OpenASIP is called Transport Ticket Architecture. Transport Ticket Architecture, or TTA, is a low-level architecture that has an exposed datapath. An example of such an architecture is presented on the right, where the programmer is able to directly move data between the function units and the register file. However, OpenASIP has been previously concentrating on customization of TTAs. In this work, we introduced a new version of the toolset 2.0 that adds support for the RISC-V instruction set architecture. With the new version, users can design RISC-V-based ASIPs with support for custom instructions that are invoked with instruction intrinsics. The toolset also ships with a retargetable compiler for RISC-V that is able to adapt to the custom instruction intrinsics. We also support hardware generation for RISC-V based on the processor description used in the toolset. In addition to RISC-V customization, we added a new hardware generation tool called Function Unit Generator that enables swift generation of hardware descriptions for both TTA and RISC-V based ASIPs. Here we can see the current RISC-V customization points available in the toolset. We support both modification of the processor microarchitecture as well as the instruction set. Microarchitectural properties are things that are not visible in the programming interface of the processor, such things like pipeline depth and operation latencies. More interestingly, we support custom instruction set extensions as well as the standard M extension. Here we can see an overview of the RISC-V customization flow in the toolset. When a processor is customized, the designer modifies an XML-based processor description called Architecture Definition File, or ADF. In this work, the architecture definition file was extended for description of RISC architectures that require more high-level properties, such as multiple instruction formats. Interestingly, in OpenASIP, the architecture definition file does not include operation descriptions. Instead, they are described in separate operation set libraries that store information about operation semantics and interfaces, such as amount of operands. The architecture definition file contains operation entries that link to their matching description in the operation set library. This way, the processor can be described in a layered fashion that allows to reuse the operation descriptions that are stored in the libraries. To support programming with custom instructions, we implemented a retargetable compiler for RISC-V. The compiler utilizes LLVM RISC-V backend and loads OpenASIP as a dynamic library together with the architecture definition file. During compilation, OpenASIP replaces the custom instruction intrinsics with instruction binaries just before code emission. Here we can see an overview of the compilation flow. Here we have some LLVM IR that has a custom instruction intrinsic. And we express the operation name as a comment because RISC-V backend cannot recognize the operation name. Then we do the backend specific phases of the compilation, such as instruction selection and register allocation. Just before code emission, we hook into the OpenASIP LLVM backend as a preemit pass. At this phase, we already have selected the instructions and allocated the registers, but we still have unprocessed custom instruction intrinsics. OpenASIP replaces these with instruction binaries that express the instruction encoding and the operand fields. After the program is compiled, we can process and link it with other tools such as binutils. And after that, we have a generic instruction image where all instructions are expressed as instruction binaries. Now more to the hardware generation and operation description side. OpenASIP has two ways of describing operations. In the first option, operations are described as a chain of already implemented operations in a directed acyclic graph. Here we have an example of this. We have some operations and immediate values, and those form a directed acyclic graph. In the second option, HDL snippet, we describe the operation with VHDL or Verilog with predefined signal names that wrap the operation. This is more low-level approach, but practical if the operation is difficult to describe as a chain of other operations. Once the operation has been described as a HDL snippet, it can be used to describe new custom operations as a part of a directed acyclic graph. These two operation description approaches are processed when the hardware is generated. Function unit generator, or FUGEN, changes operations in DAG-based operation descriptions. For the HDL snippets, the function unit generator maps the signal names in the operation descriptions to the function unit input and output ports. In addition, operation pipelines are automatically generated based on the operation latency described independently in the architecture definition file. To demonstrate the new features of the toolset, we designed a custom instruction set extension for the AES, CRC and SHA applications by using the toolset. These applications are interesting because they are cryptographic functions that include bit manipulation operations. These operations are relatively easy to implement in hardware, but they can still accelerate the target application significantly. Here on the right, we can see all the included custom operations. As the baseline for the results, we use the standard RV32IM that has no custom operations. We synthesize the designs with 28nm technology and ran the applications in RTL simulation to acquire runtime information. On average, the runtime was reduced by 44%, and in the best case, in SHA, 49%. The custom instruction set extension increased the area only by 1.5% and reduced the clock frequency by 1.4%. We could add the custom instruction set extension with little design effort thanks to the DAG-based operation descriptions and function unit generator that automatically generate the function units that implement the custom operations. In conclusion, open source hardware and RISC-V instruction set architecture have become very popular in the recent years. In addition, there is a demand for customized processors and a lack of open source tools for RISC-V customization. In this work, we introduce an open source RISC-V ASIP co-design toolset and a new hardware generation tool that generates function unit descriptions from operation descriptions. As a design case study, we created a custom instruction set extension for the AES, CRC and SHA applications. The extension reduced runtime by 44% on average, increased the area only by 1.5%, and reduced the clock frequency by only 1.4%. I want to thank the audience for your attention.